Okay, this is the last video of the final exam review. This is page 4. So now question number 35. How much of a 12 molar H3PO4 solution with 12 molar would be required to make 550 milliliters of a 9 molar solution of the same kind? So if we read carefully, it says how much of this solution. So we're actually looking for the volume that goes with the first molarity that we're given. So we're looking for V1, we're given M1, we're also given V2 and M2. So once again, M1 times V1 equals M2 times V2. We can plug in what we know. So 12 times V1 equals 9 times 550. So 9 times 550 is equal to 4,950. Is equal to 12 V1 divided by 12 on both sides. Means that V1 is equal to 412.5 milliliters. There we go. Number 3 says to increase the solubility of a gas in a solute, what could you do? So if, like a soda can, if I want to get more carbon dioxide gas into my soda, there are two things you can do. You can either lower the temperature. So lowering the temperature, notice this is of a gas. Make sure you know this for your test. Increases the solubility, or increasing the pressure. So notice these are not the same. I can either lower the temperature and make it colder. That will allow me to put more carbon dioxide gas or any gas solute into a solvent, or increasing the pressure. So increasing the pressure, I can force it into the solvent. Number 37, it says how much NH3 will dissolve in 100 grams of water at 15 degrees Celsius according to the solubility curve shown to the right. So that graph over there, you'll need to look for the line for NH3. It's this line that kind of decreases as temperature goes up. The 100 grams of water is not important. That's just this over here in the units, or in the axis label. So NH3, we look at 15 degrees Celsius, so 15 is between 10 and 20. We go up to the NH3 line, and we'll see that that's at 60 grams. 38 says what type of solution would 60 grams of KCl dissolved at 30 degrees Celsius be? So we have to find 60 grams at 30 degrees. We make a dot there, and then we compare that to the KCl line. And we can see that it's above the KCl solubility line. So anything on or above that line is saturated. Anything below it we'd call unsaturated. Number 39, the rate of solid solute. So notice number 39 is different from 36. Number 36 says gas. Number 39 says solid. The rate of a solid solute dissolving water can be increased by. So I can make my solute dissolve faster by either stirring my solution, heating the solution up, or crushing my solute into smaller pieces. All three of those will increase the rate of dissolving. 40 says for the following solutions, identify whether it's an acid or a base, and if it has more H or OH. So you need to know that acids have more H and bases have more OH. So if I have something with a pH of 3, remember your pH scale goes 0 to 14. 7 is in the middle. Acids are less than 7, bases are more than 7, and neutral is right in the middle. So if I have a pH of 3 that's less than 7, that means it's an acid, and that means that there's more H than OH. If we have a pH of exactly 7, that's not an acid or a base, that's actually neutral, and that means that I have equal amounts of both. And then if I have a pH of 13, 13 is greater than 7, that means I have a base. Bases have more OH than H. Okay, make sure you know those things for your test. Number 41 says when an acid reacts with a base, the products formed are always water and salts. This is called a neutralization reaction. And the key word there is neutral, because water is being made and water has a pH of 7. That's why it's neutral, and it's called a neutralization reaction. Number 42. The pH of a 0.025 molar KOH solution. So we're looking for pH, but we're given 0.0025 molar KOH. So if you look, this number is OH, and we want pH. So when we put the negative log of this number, 0.025, we get 2.6. But because this is OH, this is not the pH, this is the POH. So we know that pH, which is what we're actually looking for, plus the POH is always equal to 14. So pH plus 2.6 equals 14. We can subtract, that's 14, minus 2.6, the pH is equal to 11.4. So notice when they're not the same, I have OH and I want pH, they're opposites, I have to do the 14 minus my answer. Number 43 says calculate the pH of a solution of 0.1 molar HCl. So now I want to know the pH again, but I'm given 0.1 molar HCl. So this H means that they match. All I have to do is plug in pH equals the negative log of this number, and we get a pH of 1. Number 4 says, what is the difference between a weak acid and a strong acid? What pH do they have, and how do they break down? So, so remember, let's go back to our acid-base scale here for a second, right? So less than 7 was an acid, more than 7 was a base. Neutral is right in the middle. So a weak acid and a weak base are going to be closer to 7. So a weak acid would be like 5 or 6. A weak base would be like 8 or 9. A strong acid and a strong base are going to be far away from the middle. So like 1 or 2 and 13 and 14. Those are strong. And you can see from these pictures, so strong acids or bases completely dissociate. Notice none of these pieces are together. But in a weak acid, most of them stay stuck together. Only 1 or 2, very few, split apart. Okay, number 45. It says identify the Bronsted-Lowry acid, the Bronsted-Lowry base. So remember, acids are proton donors. Bases are proton acceptors. And an acid is going to turn into the conjugate base, and a base is going to turn into its conjugate acid. So if we look at the first example, we have C2H5N2 plus H2OCl makes HOCl minus plus C2H6N2. So we can see here that on the left side I have H5 and on the right side I have H6. That means that this is going to be receiving a hydrogen. Here there's H2 and there's only H1 on the right side, which means it's getting rid of a hydrogen. So we use the right side to figure out what's happening on the left. And we can see that one of these hydrogens is being donated over here. So the donor is the acid. So this is the acid. The acceptor is the base. The acid turns into this, which means this is the conjugate base. And the base turns into over here, which is the conjugate acid. Okay, and if we look at this other one, right, I have CH3OH, and then I just have CH3O, which means this H is missing. I have NH2 and NH3, which means this NH2 is going to be receiving one. So this is my acid because it's donating this last H. This is my base because it goes from 2 to 3, which means it's receiving a hydrogen. and then my base becomes the conjugate acid, and my acid becomes the conjugate base. And then the last one, identify the following as an Arrhenius acid or base. You just have to know that an Arrhenius base, the definition is that it has an OH, and an Arrhenius acid is that it has an H. That is all. That's the entire final exam review. Study and be ready for your test.